We have learned about the major transduction mechanisms that are used in 80%, 70 to 80% of microsystems over the past few lectures. Electrostatic transduction, piezoelectric, piezoresistive, thermal to some extent. And now today we are going to talk about some of these other transduction mechanisms that are still very important, but they have relatively fewer application cases. Nonetheless, there are things that you cannot do in any other way. So for example, when we talk about magnetic transduction, well, you have to have a magnetic transducer if you want to measure a magnetic field. So some of this stuff cannot be done in other transduction mechanisms, through other transduction mechanisms, and we need to learn them. And some are offering advantages in some situations that makes them superior in some particular applications compared to the ones that we already learned about. The first one we talk about is magnetic transduction. This is basically where a magnetic field interacts with how your device or part of your device is moving, right? It's the mechanical and magnetic interaction that we are mostly interested in. In terms of sensing, we are also interested in producing electrical signals due to magnetic fields and its variations. On the actuation side, what you can use is, well, the Lorentz force. From basic physics from the past, we know that if you have a charge in an electric field, you will have a force QE applied to it from the electric field. Q is the charge of the particle, E is the electric field. If the charge is moving and you have magnetic field, then you will get a second component for force that is called Lorentz force. So it is proportional to the velocity of the particle, the charge of the particle, and the magnetic field that is inside the environment. In this case, the cross product of V and B gives you the direction for the force. So V times B, and then you have a cross product force will be normal to both of them. The issue is that in most cases you don't really have a particle that is moving. Your charged particles are essentially electrons that are moving in a wire. And in a situation like that, the same equation will turn into ILB. So this is a conductor of length L, or length L of that conductor is exposed to a magnetic field B. The current direction is the direction for vector L, and B is your magnetic field in the environment. The force that is applied to that piece of conductor is ILB. Now, this is basically the foundational equation that we use to make all these electric motors, right? So we produce a magnetic field, either using permanent magnets or some current in other parts of the motor, and then the magnetic field that we produce acts upon a current that you have on your motor, on your rotor, and then you get rotation out of it. So ILB, right? So this is the important equation. As you can see immediately, this equation doesn't really scale well when you go to microscales. Electric motors need amps of current for their operation. You need permanent magnets, and to get B's on the order of 1 Tesla or so. Microscales, all of these are really difficult. You don't get a lot of current. Your typical current values are measured in milliamps or microamps. So that's a hit that you take over there. Permanent magnets cannot be integrated that easily onto a microfabrication process. You can use some from outside. You typically are limited to about, usually much less than a Tesla on the B side. And then L obviously is scaled down as well. So you get devices that are short in terms of the length of the conductor. You get less current through them, and you likely have a smaller B in the environment as well. So when it comes to magnetic actuation, it doesn't scale well. We usually do not use this kind of actuation at microscales. Macroscales, this is what moves the industrial world. The force on magnetic materials is something that we actually sometimes do use. So if you have pieces of iron or nickel attached to a cantilever. You can move a permanent magnet from outside and move the cantilever through the field produced by the magnet that you have. Compared to other actuation mechanisms, the advantage here is that magnetic fields basically go through almost all materials that are around us, right? So unless you coat something with iron or nickel or some ferromagnetic material, magnetic field goes through everything, right? So this is particularly useful in biomedical applications where you cannot put wires and energy sources inside the patient, but you still want to manipulate things that are, let's say, swimming around in your blood vessels. And those things could be, for example, markers that you are attaching to different types of cells and you want to direct them somewhere or you want to collect them somewhere. A magnetic field and a magnetic actuation in this case is very, very helpful because it lets you remotely do that. But again, this you do it on a hospital bed, not in your pocket using, a lithium-ion battery. So although that's probably more common in terms of magnetic actuation at microscales, this is probably not something that you see on a day-to-day basis. So actuation, magnetic actuation is relatively scarce at microscales. On the sensing side, however, we have a ton of magnetic microsensors and sensing technologies, each with their own advantages and obviously pros and cons. The reason for such a large variety between different magnetic sensing mechanisms is that magnetic field sensing is very important in industry. Obviously, it is important, for navigation, you need to know where the magnetic pole is so that you can navigate or correct your navigation algorithms. In a lot of cases, again, because what we just said, that magnetic fields penetrate through almost all materials, if you attach a magnet to an object, you can track it relatively accurately because that magnetic field that is produced by the object or by a magnet, you can track that using a bunch of magnetic field sensors. So in this case, for example, you can have proximity sensors that are not affected by humidity, by dirt, by grease, by any of these other things that normally disturb, let's say, an optical proximity sensor or an acoustic proximity sensor. The magnetic one is not affected by it that much. So industrially, these are very robust sensors. Because of the demand, people have found many different ways of measuring them. Hall effect sensors are probably some of the cheaper and more convenient ways of measuring magnetic field. The operation is pretty simple. Remember that if you have a charged particle in a magnetic field that is moving, that has some velocity, it will see a force as it goes through the field. Now, if you have a piece of conductive material and you send electrons from one end of this to the other end, and this piece of material is exposed to a magnetic field, the electrons will see a force that is normal to their travel path. So they will be pushed, let's say, towards the top of this structure. And therefore, over time, you will have more electrons on this side of this slab of the material or conductor than this side. Well, separation of electrons, it means that you have an electric field. You have actually a measurable electric field. So what you do is that you put two electrodes at the top and bottom of these, or on the, let's say, left and right side of this slab of conductor, and you measure a voltage that is proportional to the intensity of your field. How much? Well, this is the equation, and as you can see, RH is the property of the material, IX is the current that you pass through this, and B is your magnetic field. Another type of a sensor for magnetic field sensing is magnetoresistive or giant magnetoresistive sensors. These are sensors where you measure essentially a resistance, and the resistance value is a function of the magnetic field. A very simple case is shown here. Again, the operating principle is based on the Lorentz force you have here. You pass a current through a piece of material. On the sending side, where you send the current into the material, you have one electrode, but you collect it through a pair of split electrodes on the other side. And then if you put this inside a magnetic field, again, the electrons will see a force and they will basically deviate from their straight path of motion. And what that means is that at the output, you measure two different currents. So without a magnetic field, because of the symmetry, you will see the same current. If you have a magnetic field, one current will be larger than the other. And you can look at this as effectively having, let's say, a smaller resistance here than up there. So that's one way of doing the measurement, and it is called a magnetoresistive material sensor. Giant magnetoresistors are different. They're basically devices that are taking advantage of the quantum properties of materials and their interactions with magnetic fields. They're usually made of very thin layers of materials sandwiched or stacked on top of each other with precise thicknesses, usually only a few nanometers. And as the electrons travel through these layers, they're responding to the magnetic field from outside. And GMR effect is much, much larger than your typical MR effect, magnetoresistive effect. You can get kiloohms of change for few Gausses of change in magnetic field. Units for magnetic field, the SI unit is Tesla. The typical unit that a lot of people use is Gauss, that is 10 to the minus 4 Tesla. For reference, the magnetic field of Earth is about half a Gauss. Now, surge coil is another type of a sensor for detecting magnetic field. In this case, you use the EMF that you can have if you have a coil and the magnetic flux through the coil changes with time. You produce a voltage across that ends of that coil and that you can measure. And then if you want to intensify or amplify the signal, you can have multiple turns for that coil. So a surge coil is just that. You look at the EMF that is produced when you have a magnetic field that is changing with time. Now, that's all good and it's a linear sensor, but you don't get a lot of signal out of that mechanism. What you can do is you can make a flux gate sensor or use a flux gate sensor. These are ingenious devices. The way they work is that you have a ferromagnetic core and two coils wrapped around this core. Normally, if you have a current through the first coil, you will pick up a signal on the second coil because of the coupling between the magnetic coupling between the two coils, which is strength because of the ferromagnetic core. And the ferromagnetic cores, one of their properties is that they saturate very quickly, right? So the BH curve for the ferromagnetic curves, for ferromagnetic materials, has some saturation. So what they do here is that the current they pass through the first coil here, this drive coil here, is so large that it pushes the ferromagnetic core to its saturation limit. Once you have that saturation, or once you're near that saturation limit, because of the nonlinearity that you have between the B and H relationship, in the second coil that is picking up the magnetic field from the core, you're going to produce higher harmonics of the drive signal. So if you're driving it, let's say at 1 kilohertz, you will see the 1 kilohertz plus the 2 kilohertz signal and so on and so forth. Particularly the second harmonic is important here. What happens then is that they keep the drive signal very close to that saturation limit. The amplitude of the second harmonic will be very sensitive to where you are. And then the saturation curve, on the other hand, is affected by external DC magnetic fields. So if you have a, let's say, 1 microtesla increase in the outside magnetic field, it moves the saturation curve a tiny bit, you get a different amplitude for the second harmonic of the signal that you're picking up at the sense electrode. These devices are very, very sensitive. The good ones can measure down to nanoteslas. Typically, for example, for a Hall effect sensor or a magnetoresistive sensor, you're talking about tens of microteslas. The flux gate sensors can go down to nanotesla range. You can have sensors with optical fibers. In this case, for example, one way of making a magnetic optical sensor is that, or an optical magnetic sensor is that you can coat the fiber, the optical fiber, with magnetostatic materials. These are materials that have, let's say, magnetorestrictive, for example, materials. These are materials where they develop an internal strain if they're exposed to a magnetic field. And if that strain is transferred to an optical fiber, your optical path changes and you can detect a phase shift, for example, in response to the existence of a magnetic field. Optical sensors are usually used when you, for whatever reason, don't want to have an electrical signal when you're doing your measurement. It could be for safety reasons, it could be for convenience, and sometimes it is for parasitics and stability. Some typical applications are magnetic microsystems or magnetic microsystem applications. Well, here is a Hall effect sensor. As we saw, a Hall effect sensor is very simple. You just need a slab of conductive material and you get a voltage that is proportional to the intensity of the magnetic field, as is their minimum signal levels they can measure is about the magnetic field of the Earth. It's about, a Gauss or so, which is not good because then you have this huge interfering field from the Earth. So what they are doing here is that they actually have put some magnetic field concentrators. This is basically ferromagnetic materials that they mixed with polymers and put right on top of the Hall effect sensor. And what this does is that it acts like a lens. It focuses the magnetic field onto the Hall effect sensor, so you get a multiplication factor of, let's say, 5 or 10 or whatever, and then your sensor can basically, instead of a limit of half a Gauss for your sensor, you can maybe push it by another factor of 5 or 10. Here is a flux gate that is made using MEMS technologies. This flux gate sensor, again, you have a primary and a secondary coil. The issue is that you cannot really wrap wires around the core that easily using MEMS technologies. So in here, the process challenge is to, how do you put down the magnetic core first, and then how do you go and have wires that go from one side to the other side and then go underneath and come back so that you generate the field that you want. But it is possible nonetheless, right? And then they actually had resolutions below a microtesla with this device. And this is an interesting application of the stress that you have in these thin films. So remember that when we deposited metallic or other films, we had a stress gradient that when we released them, it caused them to curve up in most cases. Now in this case, they actually utilized that stress gradient, and they actually could close the loop and get somewhat circular coils out of this interesting stress gradient issue, which is normally a problem. So, as I said, for magnetic application or magnetic transduction, in most cases, we mean magnetic sensing, and there's a number of sensors that we talked about. The other transduction mechanism I'd like to talk about is optical transduction. Optical transduction, well, on the sensing side, there's a ton of applications, right? So you can use optical sensors to, for example, for proximity detection, to measure the intensity of light in a room, to differentiate between day and night, to adjust the illumination somewhere. There's a lot of applications for consumer. And again, if you look at communication side, all the data nowadays is transferred through optical fibers. And at the other end, at the receiver end of that optical fiber, you need to convert the optical information into electrical ones. How can we do that? Photoconductivity is a common technique. It's a cheap, inexpensive way of producing an electrical signal based on the intensity of incoming light. Semiconductors are candidates here, right? So basically what happens is that when photons come and hit a piece of semiconductor material, if they have enough energy, so they have to have the right band, photon has to have the right energy, or the semiconductor has to have the right bandwidth, band gap, so that you produce electron-hole pairs. when a photon hits the material, and therefore you increase the density of electron holes in your semiconductor, and therefore the resistance goes down, or the electrical conductivity increases. They are inexpensive, they are relatively slow and relatively noisy, but for example, the automatic lights that you have on the streets, they use a photoconductor because it doesn't really hurt anybody if they come on a few minutes earlier or later than when they're supposed to. Reflection is, in this case, what I mean is that we want to detect optical displacements using reflection. So that's a common sensing mechanism, again using optical transducers. What we do here, as shown in this schematic here, you shine a laser onto a structure that is moving in this direction, up and down. The laser is reflected back onto a photodiode. It's a split photodiode. Usually you center it at the intersection of 4 photodiodes that are made right by one by next to each other. And then if this device moves up and down, that light beam or that spot of light will move on that photodiode, and depending on the ratios of the currents that you receive from these photodiodes, you can estimate how much the device moved up and down. Extremely sensitive. So with $10 of components here, your laser and your photodiode, and then a setup to hold all of this together, you can measure nanometers of movement with some little effort. I would say not extreme amount of effort, but you have to be careful so that you get all the vibrations out. But once you do that, you can really measure nanometer levels of vibration or displacement using this technique. Interferometry is another technique that you can use to optically measure the distance or displacement movements of an object. In this case, what we have is that we send, again, a laser beam towards a device that is held like this. We are interested in displacements of this device in this direction now. When the laser leaves the fiber, because of the interface between the fiber and the wall, you have a different refractive index. A portion of it is reflected back. It goes and hits the device, and then you get another reflection there. What you do is that you go and direct these reflected waves into a photodetector. Depending on the distance between the object and the tip of the fiber, you get a different intensity, destructive or constructive combination of the two reflected lights, right? So the intensity of light that you receive here at the photodetector is going to indicate how much of a wavelength for that light is the distance between the changes in the distance between the object and the fiber. But you should see the problem right away, right? So if you go one wavelength away, you basically get the same amount of reflection or the same kind of interference. And then 2 wavelengths away, same thing. So this is good for measuring displacements that are less than 1 wavelength for your optical beam, meaning that, again, nanometer levels of accuracy is relatively easy to achieve here. On the actuation side, well, there is one thing that we want to produce light in response to your electrical signal, and that is normally done using LEDs or lasers at microscales. So, again, you've seen tons of examples like this. I'm not going to go through that. You can also heat up, like the old light bulbs, you can heat up a resistor and start to produce light in visible wavelengths. That's not done as commonly, but there are certain applications that actually need that kind of a light. Maybe you want a lot of IR in your output spectrum. You can use an optical beam, a light beam, to move stuff. And then the easiest way of doing that is that if you have an object, you go and shine a light beam at the corner of this object, but the beam or the light is chosen such that when it hits the device here or when it hits the structure here, it is absorbed by the material here. And then what that does is that you produce heat locally. And now through an indirect method, the heat you produce here is going to cause the material to expand, and therefore you will have a mechanical stress, and therefore you can move stuff. So that's relatively easy to understand and easy to do, and you can actually cause a DC movement or modulated movement of an object remotely this way. You can also have momentum transfer, right? So this is the momentum transfer between your beam of light and the object, the particles or objects nearby. This is very common, especially in biomedical applications, where you can actually, and you can just look up the word optical tweezers. You can go and use light to grab onto, for example, a cell and bring it to a portion of your microfluidic chip where you want to do some sort of an analysis on it. You don't want to mechanically touch it, but what you do is that you go and use the optical pressure from a beam of light to move the object from one, or in this case a cell, from one corner of a chamber to another. So that's that. Another transduction mechanism that is extremely sensitive is called tunneling. What happens in this case is that, unlike or despite the prediction of classical physics that says as long as you have a physical separation between two objects, the current cannot flow between them, a DC current cannot flow between them, quantum mechanics actually contradicts that. So it says that if you have two conductive objects close enough to each other, electrons can jump over that barrier, which is the gap between them, and move from one conductor to the other. So you get a DC current, even though the two are not touching. However, for that to happen, you need to be within a couple of nanometers. The two objects have to be within a couple of nanometers of each other. And obviously, as you might guess, the current that you get is going to depend on a bunch of factors. The most important one is gap. So the gap has to be on the order of a nanometer or two. The other one is that the surface properties. Let's say if you have oxides on the surface of these materials, that's going to add to your barrier height, the barrier that the electron has to jump from one side to the other. So you want these surfaces to be really, really clean and conductive. And also the geometry of the tip, right? So if you put the two parallel plates very close to each other versus a sharp tip, well, obviously you can get more current from the sharp tip than a parallel plate. So geometry, type of material, and gap are the ones that are determining this tunneling current. We say tunneling because the electron goes through that gap, tunnels through the gap. There's no physical medium for the electron to travel through. And your gap is a couple of nanometers. This thing can measure sub-nanometer displacements very easily. You get huge changes, exponential changes in current with a very small change in height gap. And it was therefore used as a surface, in surface tunneling microscope, where you held the tip really close to the surface, and the changes in the current as you moved it around told you about the topography on the structure below, on the material below. And again, do a search on a scanning tunneling microscopy. You can see that people could actually identify layers of, for example, single mono layers of materials on top of each other. As I said, it's a fairly easy technique. The first time that they did it in front of me, it was an STM, and they took a piece of carbon and they could actually show the carbon atoms in that piece of graphite, which is amazing to me. Now, but again, the setup was fairly cheap as long as you know how to manage the vibrations in the environment. So these are the main transduction mechanisms that I wanted to discuss. One more thing that we would like to go over is resonance. As a transduction mechanism, resonance can be one of the most accurate and precise methods that is available to you. So what is resonant transduction? So remember that we had a massive spring system like this here. You got a resonant frequency that was proportional to your mass and spring, as shown here. And there is some damping mechanism in the environment that can come from friction with air, can come from support losses, all sorts of mechanisms can contribute to losses here, but you have some damper in your system as well. In this simple case, you can write the equations of motion and take the Laplace transform, and at the end of the story, show the equation of motion as this, right? And we've gone through this through the dynamic section of the course, so I'm not going to repeat it. As you reduce the amount of damping in your system, we'll get a sharper and sharper peak in our frequency response. Now, this is what we like. That for a high Q device, for a device that has very little damping, I get this really sharp peak in the frequency response of the system. Again, going back to our dynamic lecture, I know that the signal peak here, the magnitude of the displacement, is Q times what I have at low frequencies. So if Q is 1,000, at resonance, my displacement for the same input force amplitude is 1,000 times larger. That's great if I'm doing resonant actuation. But in resonance sensing, what I do is that since I have this sharp peak in frequency response, I can very, very accurately figure out if that peak has moved to the left or right, if the frequency of my resonance frequency of my device has changed. So if I come up with methods that affect the resonant frequency of the device, I can very, very accurately monitor their influence on the resonance frequency. I can measure the resonance frequency very, very accurately. The reason that I can do that very accurately is two things. First of all, measurement of a frequency is relatively easy, right? So if you want to measure the frequency of a signal, for example, the easiest thing you can do is that you can define a time window and see how many cycles of that signal happen to be in that time window. Any microcontroller can do that, right? There are more precise ways of doing it, but for example, this was just one example. Once we do that, we can be easily, again, certain of the value of that frequency. So let's say if you're measuring the frequency of a 1 megahertz signal, I can provide 4, 5, 6 digits of accuracy depending on the application to you relatively easily. And what lets me do that is the availability of very good frequency references. A quartz crystal that you pick up from the market for a few dollars, maybe even less than $1, is stable down to the 4th or 5th digit after the decimal point for the frequency, right? So it is like 10.0000 megahertz, the resonance frequency of that. Once you have such a good reference, you can measure everything else relative, or the frequency of something else relative to that reference easily. We don't have that kind of a freedom in terms of, let's say, temperature references, voltage references, current references. All of those are significantly less accurate than frequency references that we can have. And in actually many cases, the best temperature references that you have or the best voltage references that you have are tied to a frequency reference. And so measurement of frequency is easy, changes in frequency, again, relatively easy, and you can be certain about the value of those frequencies that you measure. So therefore, resonance sensing is both accurate and precise. Precise meaning low noise, accurate means calibrated. You can actually have some certainty in the value that you're reporting. And a resonance sensor, therefore, in most cases is your more accurate or more precise sensor compared to other types. In some limited cases, you actually look at the changes in Q as the sensing mechanism, but this is less common because Q is affected by so many different factors. For most resonance sensor applications, we look at the changes in the mass or the changes in the spring constant. So how does it work? So let's say if you have some additional mass in your system for whatever reason, your resonant frequency will change. The effective mass of your system has changed by delta M, and you can show that the resonant frequency will change. It will go down always, and your sensitivity is given by this expression over here, right? Now, where do I use this? There are a lot of gas sensors that operate based on this principle, where you have a resonator where one surface is covered by something that absorbs a certain type of gas. Once that gas is absorbed to that surface, the mass of the effective mass of the structure changes, and you can estimate how many molecules were absorbed, and therefore what is the concentration of that gas in the environment. In biomedical applications, there is a lot of situations where you would like to weigh the cells or bacteria, and this is the way that you do it. You can also look at the change in the spring constant of the structure, or effective spring constant of the structure. And again, if you do the math, the sensitivity is proportional to your initial resonant frequency divided by the stiffness, the initial stiffness of the material. Again, because we can measure the changes in frequency so precisely, this can be very, very sensitive. How does that work? Well, again, remember the guitar string example. You put a little bit more tension on it, the resonant frequency goes up. You reduce the tension, the resonant frequency goes down. And with resonance, we've had a lot of devices. There's a ton of resonant devices out there because it is just such a convenient method to achieve large accuracy, high accuracy and precision. So here are a couple of examples. We'll cover them in detail a little bit later. But here's the resonant pressure sensor, where the pressure changes were converted into frequency changes, and that was sent out for readout by an electrical system. This one has a resonant actuator on it. So we actually take advantage of resonance again, but what we do is that we have a small driving force. By operating the device at its resonance, or a high Q of, let's say, 500, we get 500 times more displacement for that same drive signal. And this one was a mass sensor where you could actually go and measure less than the mass changes due to less than a single monolayer of a metal deposited on that structure. In this case, the resonator was a square plate resonator operating in its bulk extensional mode. So the magnetic field sensor, this resonant actuator, so let's just have a look at it. In this case, the idea was that we wanted to have the smallest drive signal because of the interference challenges that we had in this sensing method. Okay, so the movie is not playing, but we have seen this before when we talked about the thermal actuators, right? In the thermal actuator side, we talked about, the chevron actuator that is at the corner of this device, and it produces a tiny displacement. By operating the device at resonance, I could get a significantly larger amount of displacement for a smaller input signal. So that's that for transduction mechanisms that we wanted to discuss in this course. There's a couple of final wrap-up points, let's say, that I want to mention, and then we'll be done with this section of the course as well. The first thing is electric circuit representation. So we have these mass spring systems in mechanical domain. We saw that the operation or the behavior of this system is governed by a second order differential equation. You have RLCs in electrical domain, and again, in this case, you can show that the voltage current relationship for this circuit is governed by a second order differential equation as well. So by just playing with the variables here, we can make the, let's say, current and voltages in the system below to represent, let's say, forces and displacements in the system above, in the mechanical system above, and just change the variables and do that. There is a better way of doing it where you go and look at this from the energy point of view. At the end of the story, the goal here is to come up with an equivalent electrical model for your mechanical system. Why would I want to do that? Well, one reason that MEMS engineers liked it in the beginning was that a lot of the MEMS engineers in the beginning were electrical engineers. They understood electrical systems better than they did with mechanical systems. And the mechanical systems that we're dealing with at MEMS domain are fairly simple, right? A mass spring system essentially summarizes most of them in many cases. So this was easy. They could go from a mastering system into an electrical system and understand how that system works. More importantly, once you have an electrical model of the system, you actually have access to the electrical circuit simulation tools. And there are things that electrical engineers do and need to know, and especially when they design a system that has mechanical and electrical components together, where mechanical engineers traditionally didn't have to. So for example, one is the effects of noise and noise multiplexing and things like that. All of those were big concerns in electric systems and electronic systems, not so much in mechanical systems. By having a electrical representation of that mechanical system, I can now do those kinds of analysis on my micro mechanical device. Also, I can now, traditionally, I designed an electronic circuit and did all my simulations in SPICE-based simulators. And I designed my mechanical system and did all my simulations and verifications here in, let's say, in finite element-based methods. And then what I did is that I tried to figure out what the response of the system here is and use equivalent, let's say, voltage or current sources in the electrical simulator to simulate the behavior of the structure. If I can come up with an electrical equivalent of my mechanical system, I can do a co-simulation. I can do simulations where I can see the interaction between the two domains at the same time. And we often start with a basic model for the mechanical system, going through a conversion that I'm just going to show you in a second, and then you can go and fine-tune it based on experiments or finite element simulations and optimize it. Another related technique is reduced order modeling, where you go and break down a complicated mechanical system into a fairly simple model, and then you use that in your electronic systems. And another good thing about coming up with an electrical equivalent model of a mechanical system is that you can take into account the effect of electrical parasitics in your system. These microsystems that we make, you have electrical pads for actuation, for sensing, grounds, all those things around this. And all these pads and electrical connections, at the very least, are coupled to each other through capacitances, parasitic capacitances that you have through the air or through the substrate or through the package. And by having an electrical model of the mechanical system, you can add those parasitics to it relatively easily, and your electronic system, at least the model, sees a more realistic model of what it will eventually deal with in real life. And on the mechanical side, you can have transductions, right? So you can have transduction from mechanical to electrostatic, from let's say voltage on the electrostatic side to a force on the mechanical side. Or let's say piezo junction effect, you have stress on the mechanical side changing the current on the electrical side. These conversions between different physical domains, when you go down to electrical circuit representation, are usually done by using transformers with the correct winding ratios. So you go from, let's say, a voltage in the electrical domain through a transformer, and you produce a force in the mechanical domain. And now the transformer on the other side, where you have the master spring system, instead of the master spring system, you put your RLC that represent the master spring system. And then maybe you have additional transformers to take back the output from the mechanical system and maybe produce a current, for example, in response. So there are different ways of converting mechanical and electrical components to each other. A typical approach is this. So on the left side here, you see mechanical elements or quantities, and then the electrical quantities are listed on the right. So a force is converted to a voltage, velocity to a current, and so on and so forth. And for example, if you want to go to thermal domain, you get a similar situation. You can go and convert a thermal circuit into an electrical circuit if you follow these conversions. Now, when you're building the electric circuit that represents a mechanical system, you have to make sure that, these conversions in electrical systems, you can put the components in parallel with each other, in series with each other. How you connect these components to each other depends on, your flow variables. For example, if the devices see the same displacement, like the mass that is moving and then it is stretching a spring with it, they should have the same velocity, therefore they should have the same current, meaning that you put them in series in your electrical domain, and so on and so forth. Last slide here is an example. This is a resonant sensor. In this case, what we do is that we have an electrostatic port here at the input. We have a shuttle here. We have seen a similar device, but what we do is that we force this piece into resonance at its resonant frequency by applying a voltage proper DC and AC combination here, and then we monitor that movement using the second electrode here. We've seen a device like this before. Now the issue here is that once this device is operating at its resonant frequency, if you add mass to the center part here, the resonant frequency will change. Now the question here is, what is the mass sensitivity of the device? What is the required DC voltage to get a certain amount of displacement at resonance? And how much current do you produce at the output under those conditions? An equivalent circuit model for the device. So the first part is easy. We need to go and find the resonant frequency of the structure. We have an estimate for the mass, ignoring the mass of the beams. We can only keep the mass of the shuttle as the effective mass of the structure, and therefore, knowing we have two clamp-guided beams on these two sides, estimate the stiffness, therefore the resonant frequency, and therefore the mass sensitivity from the equations I showed you before. The DC voltage that we need to create that much displacement at resonance with a given Q here, well, what I need to do is that I need to go and figure out what is the force that gives me that displacement. At resonance with a Q of 15,000, it means that I need to find a VDC VAC times, let me just maybe write it again here. This is similar to what we discussed during the electrostatic transduction discussion, but we said that if you have a combination of DC and AC signals, the electrostatic force is dx or dy depending on the direction, but VAC sine omega t plus some VDC squared, right? And if you're focusing on the harmonic force, basically the force that is at the same frequency as your drive signal, you can show that at omega, your frequency, so let's just call it FH, F harmonic is 1/2 dC over dx, whatever, or dy, times 2 VAC VDC sine omega t. Okay? And if you're interested in amplitude only, so the harmonic force amplitude, the twos cancel, is going to be VAC VDC. So the product of these two times the rate of change in capacitance. So this is the equation that gives you the magnitude of the force at resonance. This behaves as Q times larger. So what you can do is that you can go and figure out how much that force should be, because I know the stiffness of the structure, calculate the force, and then come back and plug it into this equation to figure out the DC voltage. Magnitude of the output current, if you figure out how much the electrode is moving up and down, and you know the DC voltage, again, we've done that calculation before, you can go and figure out how much is the output current magnitude, and then the electric equivalent circuit is found through the method that we discussed before. I have the number for the resonant frequency. So resonant frequency, if you do the calculation, is about 90 kilohertz. And the rest of these calculations, if you folks need to do it together, we can go through it during one of the live sessions that we will have. With that, this is the conclusion of the transduction section for this course. Over the next couple of lecture videos, the 3 following lecture videos, what I'm going to do is that I'm going to focus on some device examples and show you how they are made, the structure, the transduction that is used, and that will be it basically for you to understand the differences, let's say, between different types of accelerometers or pressure sensors or microphones. And for you as a user, the next thing to do is to interface with them and process the signals from them. So after we see how some examples of these micro devices, we'll talk about interfacing and signal processing in the remaining 2 segments of the course. So that's it for today. Thank you very much, and I'll see you in the next lecture.